Okay, here we go. Chapter 1 in CE, Matter and Measurement. We're going to go through it pretty fast. This first part is pretty easy. So in chemistry is the science of everyday experience. So chemistry is the study of matter, its composition, its properties, and its transformations. That's what chemistry is. So chemistry is also known as the central science. Why? Because other sciences demand an understanding of basic chemical principles, and chemistry is often referred to as the central science because everything refers back to chemistry. So let's go ahead and watch this little video.
Hey, what's matter? No, not what's the matter. Obviously, since you're here with me, you're pretty awesome at the moment. You might have heard that everything is made of matter, and that's true. You, soccer balls, iPads, even your pet Fluffy, all made of matter. So that's interesting. But what is matter exactly? The scientific answer is matter is anything that has weight and takes up space. You already know about weight, right? That's just how heavy something is. Like if you've ever been to a doctor's office, the first thing they do is have you stand on the scale so they can measure how much you weigh. As for taking up space, another way of thinking about it is that all matter has volume. It simply fills the area it's in. When you pour water into a glass, for example, the water's volume is the amount of space that it takes up in the glass. So all matter has volume and weight. But it sure doesn't all look the same. Well, that's because matter comes in different forms, or states. Liquids are a state of matter that I'm sure you're familiar with. If you've ever poured yourself a drink while trying to watch TV, you might have noticed that liquids take up space, because once the space inside your glass is full, right on the carpet. Sorry, Mom. You also know that water has weight if you carry a water bottle. As you drink from it, it gets lighter because you're removing water from it. Solids are matter too, of course, probably the most obvious kind. Rocks are solid, and so is ice, which is just solid water. Soccer balls are solid, iPads, your pet Fluffy, and every single guy in One Direction. And just like rocks, all those things have weight and take up space. Now, you know what's weird? Sometimes matter can't be seen or felt, but it's there. Like the air we breathe. Air is an example of gas, the third main state of matter. And I probably know what you're thinking. How do we know air, or any gas really, is there if we can't see it? Well, we can prove it by doing an experiment. Science. Let's start by asking the question, is air matter? Because if it is, it should take up space and have weight, right? To see if air takes up space, look it, I can easily drop an empty balloon into this little box, but a full one won't fit. That's because the air that fills the space inside the balloon is bigger than the space inside the box. Now, does air have weight? Let's try something else. Take 2 empty balloons and tape them to the ends of a meter stick. Then we'll hang the meter stick on a string so that it's perfectly balanced. Now let's see what happens if we blow up just one of the balloons and put it back on our meter stick. Check it out. The end with the full balloon sinks. It weighs more than the empty balloon because the air gives it extra weight. The balloon full of air will always weigh more than the empty one because air is matter and matter has weight and takes up space, whether it's a liquid, a solid, or a gas. So listen, the next time someone tells you that something doesn't matter, you can tell them to their face that technically everything is matter. And tell them Sabrina said so.
Okay, so, whoops, let me get there. The next thing that we need to talk about is just states of matter. Basically, this goes really fast because we already talked about it in it. Solid is rigid, it has a fixed shape and a fixed volume. Liquid's not rigid, it has no fixed shape, and it has a fixed volume because it's usually contained. But it can take the shape of anything that it goes into. Gas is not rigid, no fixed shape, and no fixed volume. So, other things that we need to worry about are physical versus chemical properties. So, and this can do with changes too. So physical properties are things that you can describe about it without changing anything. So the color, the shape, the size, the density, the amount, the volume. But chemical properties are how flammable is it? Does it rust? Does it burn? Is it corrosive? And what's its reactivity with other chemicals? Now changes are just twisting that a little bit. Physical changes can easily be reversed. There's no new product and often just the state changes like ice melting or freezing. Chemical changes are not easily reproduced. That's like wood burning. I get coal or I get ash. New products are formed. Reactants are used up. Often heat, light, sound, fizzing, something is going on. Electricity may be produced or a precipitate may form. Okay, some other examples of physical properties and physical changes, looking at the two together. So physical properties, physical change, so boiling point, boiling, freezing point, freezing, melting point, melting, condensation, you get the idea. Okay, so ductility is ability to be stretched into the wire. Malleability is how you can hammer it into a sheet. Solubility is dissolving, and electroconductivity is moving the electrons. As we look at chemical properties and change, a chemical property is the ability of a substance to react with or transform into another substance. So here's a chemical change where I have mercury thiocyanide and I heat it up and the bonds are broken and I make mercury sulfide and carbon disulfide and tricarbon nitride. So we get new substances. Chemical changes, the way that I can know that something has changed. The color changes, the odor changes, it produces heat, it produces cold, fizzing, foaming, bubbling, sound produced, light being given off, a precipitate formed, oxidation or rust or tarnishing. So those are all ways that we can identify chemical change. As we look at classification of matter, this is a nice little tree here that helps us to understand how matter is classified. And by the way, anytime you can stop this, you can pause it, you can rewind it. There's a study guide that goes along with it. I would make sure that you keep that study guide because there is a year-end test and that study guide is going to be something you can go back and look at and review for the test. So we start with matter. Just like the video said, everything's made up of matter. For matter, we can break it down into pure substances or mixtures. Let's go pure substances first. From pure substances, we can get elements. This is what is on the periodic table, the elements of the periodic table. Compounds are one or two or three or four of those elements combined as one thing. So like this would be a representation of SiO2. Okay, so that would be sand. On the other side here we've got mixtures. So on mixtures we can have a homogeneous mixture or a heterogeneous mixture. A homogeneous mixture is the same throughout. No matter what part I take of it, I get the same. So if you've made Kool-Aid correctly or made a soft drink where you have to put powder in and stir it up, if you've mixed it all the way, then it should be the same throughout. The first glass should taste like the last glass. A heterogeneous mixture, though, is where I can pull out different samples and have different things. A good example here would be like granite or any rock, because usually the rock is not the same all the way through. So let's look at some other things that we can look at here. So does it have a different composition throughout? If it does, you go to mixture. If it doesn't, it's a pure substance. Can I separate it into pure, simpler substances? In other words, can I separate it into elements? If not, it's an element. If I can, it's a compound. But to go from a compound to an element, I have to chemically separate it. Okay, so it gives you some examples down here at the bottom. For a mixture, I need to look at, is it the same throughout? That's homogeneous. If it's not, it's different throughout, like seawater or salt water that is really heavy, then it is not. It's heterogeneous. So another look at another chart, to get from a mixture to a pure substance, you can physically separate it. So if I had sand and iron together in a mixture that was heterogeneous, I could use a magnet to separate it and physically change, pull out the iron, pull out the sand. But a chemical compound, I can't. So if I have NaCl, in order to separate it into sodium and chloride, I'm going to have to do some kind of chemical change. Another look at the matter diagram. You need to be able to identify what do you have. So here's some more examples that you can look at. Okay, then we get to the metric system. In the metric system, this is something that you've done since forever. This is just a little quick thing. King Henry doesn't usually drink chocolate milk. It says unusually. It should be usually. So you can look at how this chart works. Basically, you've moved the decimal one way or another. You can also use this way. Like I said, you move for smaller units, you move the decimal, making it big, making the number bigger. If you're moving from a small unit to a large unit, you move it so the number gets smaller. Some of the conversions that we use, prefixes here, we usually use kilo a lot, the base unit, meter, liter, gram. We use centi, milli, micro, and nano a lot. The others not so much. Giga only when it gets really high, and mega same thing. So the center point here would be like a meter or a gram or a liter, and you go from there. This gives you the symbol to start with. Micro looks like a U, but it's a fancy M. And we never use the female and atto, hardly ever. Another look at it. This is with it in scientific notation over here on the side. We'll talk about that in a second. So measuring. When you use something to measure, you usually use a meter or centimeter, and you're wanting to estimate in between the lines. So for instance, if I had 49.5 and it was in between 0.5 and 0.6, I would estimate that last one, and we'll talk about that in a little bit. To measure mass, we're going to need to know sort of in our head how much something weighs. Now if I look at a normal size paper clip, that weighs about 1 gram. So I can sort of say, oh, if it's 10 grams of sugar in this soda pop, that's like 10 paper clips of sugar. A kilogram weighs about the size of a regular size textbook. If you can sort of get an idea there. We're going to be measuring mass with triple beam balances and with electronic balances. So I don't know how many of you are familiar with triple beam balances, but that's one of the requirements for the college, that you use a triple beam balance. So you're going to place something on the scale. Before you do, you need to make sure all these little slides are at 0 and that this right here is lined up right on the line. If it's not, then the scale is off and we need to recalibrate it if we can. If not, you'll have to grab another one. Some of ours are really old and have a hard time there. And what you do is you move the biggest one first until you get so the next one up, the arm here goes down, and you put it back so it's still up, and then you move the next biggest until you finally get that even, and then you just read as you go. And we'll go over that more in lab. Okay, as you talk about weight versus mass, a lot of people use those two words as the same thing, but they're not. Weight actually has the gravity on a mass. So your mass always stays the same. It doesn't matter if you're on the moon or in the earth or on Mars. It doesn't matter. Your mass is always the same. But your weight changes depending on the force of gravity on you. And so when we talk about weight, we're usually talking about newtons. When we're talking about mass, we're talking about kilograms. Now, most of the time when we're on Earth, we just refer to things as kilograms because the gravity will be the same no matter what. Okay. The last thing today we're going to talk about is measuring in volume. Remember, when you do a volume of something, it's length times width times height for a square or a cube or rectangle. Very easy to do. When we're measuring volume, we're going to be using what's called the meniscus. The meniscus is that bottom part of the liquid that you can see right here. And we're wanting to read at that lowest level. That's what the meniscus is. It's the concave part of the water bubble. So here we would read 40, 1, 2, and then it would be 3. And since it's right on that 3, we would put 0.0. We always want to estimate one more past what we know for sure. When we measure something that's irregular, as long as it's not soluble in water, we can take and measure some water, put the object in, measure some water, and then subtract the two, and that is the difference. And we call that volume by displacement. So this one, if you're looking at it, it's just over, let's see, 1, 2, 3, 4, 5. So each of these are 25, 25, 50, 70, 25, 50. There's 100 divided by 520. There we go. 20, 40, 60. So it's about 260 and 200. So 260 minus 200 is 60 for the volume. And that's because this is not very easily read from far away. When we're looking at volume, 1 centimeter cubed, 1 centimeter by 1 centimeter by 1 centimeter, is equal to 1 milliliter. Often in medical, it's called 1 cc. Cubic centimeter. 1 decimeter cubed is equal to a liter. Some other formulas that you'll need to know, like a rectangle, base times height, a triangle, base times height divided by 2, eclipse, you can do that, a trapezoid. Those are ones we don't use very much in chemistry, but sphere we use, cylinder, cube, and prism for volume we will use. So make sure you're familiar with those. So let's do an example here. Here we have a petri dish, and it has a radius of 7.50 centimeters, and we want to fill that to the depth of 2.5 centimeters. What volume in milliliters would be required? What about liters? So this is the equation from the last slide for a cylinder, and so if we plug in what we have, and since we have a radius, we're going to times that radius by 2. So as I put this in, this is my radius times 2 here, and I've squared it. So I'm going to plug that into my calculator really quickly, and I get this answer. Now notice I only have used 2 significant figures and then have this as a 0 because I only have 2 significant figures here, and we'll go over that more in a little bit. So here, if I have 76,500 microliters of milk and that needed to be consumed in one day, could it be done easily with lots of effort or not at all? The easiest thing is to change those microliters into liters. So, by the way, centimeters cubed is equal to milliliters, and if I wanted to change it to liters up here, I forgot, 0.44. So down here, we're going to use dimensional analysis to do this. Instead of doing the times and parentheses and that, this vertical line represents a times, the horizontal line represents divide. So we start with what we're given, we don't put anything on the bottom, and then we say, oh, there's 10 to the 6 microliters in 1 liter. Now I can cancel out microliters, and I'm going to take 76,500 times 1 divided by 10 to the 6th, and I get this for liters. Now if I compare it to something that I know, like a 2-liter bottle of pop, 0.07 liters is nothing. It's not even a part of it. So remember, that's 2 liters of pop. So this would be easy to be able to drink that much milk in one day, because divide that in half, that's 1 liter, and then it would just be a little bit down here in the bottom. Okay, so now we're going to get to significant figures, and I'm going to stop this video, and the next day is where we're going to do this.